Thanks, Jenny, for your kind introduction. So yeah, my name is Lena. I, as Jenny, also work at BAM in Berlin. And today I will talk about our project, which we call PAVER. So you can see the logo on top of the slide. And the question is, how will we explore, work, and even live on the moon? So yeah, as Jenny already said, we have different focus areas at BAM. So this project is based in the focus area of materials, where we look at innovative materials, but also specific processes, degradation, and also life cycle of components. So at BAM, we have a competence center for additive manufacturing, which is called AM at BAM. If you scan this little code, you will be guided to the page on our BAM website. And basically in this competence center, we bundle all the experience we have at BAM in the area of additive manufacturing. So additive manufacturing can also be called 3D printing. And if we think about working and living in space, 3D printing actually is a very nice opportunity to process materials because it can be a very autonomous process without a lot of human interaction needed. We can create computer-based models that we, for example, send from the Earth to the moon, and the printers will just do the job for us. So this is a very interesting process when we think about autonomous manufacturing. And the project is also based in the section of materials because we look at a very innovative material when we think about living on the moon. Obviously, on the lunar surface, we have the lunar dust, which is also called lunar regolith. Here on Earth, we have about 300 kilograms were taken back from the Apollo missions. Obviously, for all the research projects that are going on Earth, we can't use the samples from Apollo, but that's why we constantly look at creating similar materials that are called lunar regolith simulants. And we look at how we can process these ones because they are as close as possible to what we would expect on the moon. So just looking a little bit more at 3D printing, this is an image from our BAM yearly report. So at BAM, we have a very interdisciplinary team from additive manufacturing technology, materials analysis, but also destructive and non-destructive material testing. We look at safety and quality of our products. And as I already said, we investigate innovative materials, manufacturing processes, and testing methods. What we can also do in this competence center is advise on material selection and processes and comprehensive testing to get the best out of the product. And the close connection between government, industry, and research allows us to transfer our research and our work quickly into production. And one of the main aspects is also monitoring. So if we want to have an autonomous process, we want to have a digitally monitored additive manufacturing chain and, for example, detect defects like cracks in real time, as you can see in this picture. So now let's talk about the moon. Our project, as I said, is called PAVER. It's funded by the European Space Agency, and we have a couple of universities, Technical University Clausthal and Hochschule Aalen, that work with us on this project, and also an industry partner, Liquifer Systems Group from Austria. And yeah, on this slide, I just mentioned all the partners that are involved in this project. What's the motivation for this work? So if you look at this image, you see an astronaut from the Apollo 17 mission who just came back into the Challenger module after walking on the moon, and maybe working, but mainly walking. And his clothes are covered in dust, but not only his clothes, also his shirt and his face even. So this is something that we really want to avoid in the future, especially when we want to establish a more permanent presence on the moon. So if we look at what we have to do to establish a lunar base or moon village, and we have to go through different infrastructure development phases. So here you can see that even if we want to stay shorter than 2 weeks for example, research purposes, we already need to have fully automated processes for infrastructure, such as landing pads to enable safe landing of vehicles, but also main roads, so that we can prevent this dust creation. So this is something that already needs to be done quite early, the infrastructure preparation. Then in the middle, we have the aspect of sustainability. So what do we have to do if we want to stay, for example, longer than a month? We need to have a further developed infrastructure of roads, but also already operation pads and infrastructure for machinery and telescopes, because we don't just want to be there, we also want to work and investigate and do research. So this is something that we have to do in the medium term. And in the long term, if we want to get to an operational phase, we really need to have a finalized infrastructure, and we need to be able to extend this infrastructure and any other structures with building blocks and habitats where we then can actually live as well. So to be able to do this, at the beginning of this project, we also looked at creating a roadmap. So what are the missions in Europe with the European Space Agency, but also internationally for future lunar technology demonstration missions? In which mission could we potentially integrate our project in the future? And what are the steps that we need to take to develop this project towards a demonstration mission? So this brings me to the next slide, where you see it's the same image, but we basically want to enable on-demand construction and manufacturing in space. And in this talk, I'm going to talk about large infrastructure elements. As I said at the previous slide, we talk about main roads, landing pads, and large elements to create these structures. On the left side of the slide, you can also see small tools that are printed from metal. This is another project we have at BAM. But yeah, in this talk, we're really going to focus on large elements that we want to 3D print with possibly the lunar regolith that's available on the surface of the moon. So what has already been done, and what do we now want to do to build up on this previous projects? So on this slide, you see a visualization from the project Urban on the left side. They looked, it was a European Space Agency contracted project, and they looked at developing a lunar base using 3D printing technologies, and how this lunar base in its final operational status could become independent from transport from Earth. So basically an autonomous lunar base. So this was a study. And then afterwards, there was the European Horizon project regolith on the right side, which aimed at advancing automation in sintering of building elements for habitats and shelters. So if we talk about lunar dust, obviously this is a very powdery material, and there are different ways of compacting this material. If we talk about sintering or melting, that means that we take a very high energy source to melt or sinter the particles together. There are also different technologies, such as bringing in chemicals or binder or water-based binder to be able to then put the particles together and deposit them. However, in this project and also in our project, we looked at potentially using the energy of the sun. I'll get to that in the next slide. So in this regolith project, they looked at this automation aspect of compacting regolith using sintering technologies. So there was also another study which was called SMARTY, that wanted to look at Internet of Things and connectivity, which is also really important. So what we learned from this project, that the creation of essential infrastructure, even before building habitats and bigger structures, is really important. And a study was needed for the sintering and melting, as I said, of lunar regolith for large paving areas to create the road infrastructure for future operations. We aimed to have a fully automated process and to use, as I said, the regolith in its powder form and 3D printing so that we don't have a need for a binder and additives. And in the long term, this should reduce the urgency for material transportation from Earth. So as I already said, we want to use the powder or the lunar dust on the moon, and we want to use the sun. And on the moon, we can do this because the moon, it doesn't really have an atmosphere. It's very, 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 very thin, but not even really existent, which means that we get a lot more energy from the sun that we get on Earth. And if we collect the energy of the sun and bundle it, for example, with mirrors, we can we'd actually be able to do melting of this lunar regolith or lunar dust using only the resources that are available on the moon. And this is called in situ resource utilization. And yeah, you can see an image from NASA on the right side. And when they speak about ISRU, they say when NASA returns to the moon with the Artemis program, they plan to put in place sustainable infrastructure that will allow to explore and study more of the moon than ever before and get ready for human exploration of Mars. To live and work in deep space for months or years may mean that astronauts have less immediate access to supplies. NASA will send cargo to the Gateway, which will be another space station that orbits the moon. Will send cargo to the Gateway to support expeditions to the surface of the moon. However, the farther humans go into deep space, the more important it will be to generate products with local materials, a practice called in situ resource utilization. And this is what we want to work towards too. So if we now look at how to actually pave a road, as I said, I have another slide on 3D printing in detail, but we want to use this technology and we want to use the lunar dust or the simulant that we have. And in this project, we looked at different setups. So a more stationary setup on the top left and a mobile setup on the top right of the slide. In both cases, we'd on the moon probably still need a rover to transport things from A to B or to move around on the surface of the moon to pave the surface immediately. However, we also needed to look at what we have available for this project in at BAM and with our partners. And on the bottom of the slide, you can see a bit of an evolution that we went from sintering just a very compact amount of powder to moving a box with the powder under the laser spot. And in this case, we actually have to use a very high power laser to simulate the sun. It's a bit funny, we always simulate the things that we don't have on Earth, but that we have on the moon. But yeah, we need to have this high amount of energy, so we have a powerful laser. So yeah, the box was moving under the laser so that we have a bit of a mobile setup. And later on, we also had a robot that was generating additional layers of powder so that we can have a layer by layer process, which is actually what 3D printing is about. So yeah, I just have one slide on 3D printing, just so that you have an image as well. So we have a material on the left side that goes into the process, and the process consists of a unit that deposits the powder on top of a build plate. And as I said before, we do this layer by layer, which explains the term additive as well. And then each layer is actually then, so we have a computer model, a 3D model of a part that we want to create. For example, here in the middle, it's very boring, but on the right side, we'd have this 3D model of a wrench, for example, and this goes into the system. And then in each layer, we write the information from the model with, in this case, a laser. So this is then a step-by-step process. And in the next slide, I have some images from our experimental setup. On the left side, you can see the laser and the robot that's holding this box with our Lunar simulant and is moving under the laser. Then in the middle, we have at the beginning our mobile setup, where later on I have an image where the robot is then moving the box in this setup. And on the right side, we have this other robot that is meant to deposit additional layers of simulants so that we can actually build up a structure. So I hope that this video works, looks good. So this was just at the beginning of our project where we didn't have any mobile setup available. So we just had a box with a lot of simulant material, and we fired the laser into the powder bed, and you can see how it's now slowly cooling down. The process is very hot, so the temperature at the surface is, I think, between 900 and 1000 degrees Celsius. So the temperature in the melt will be even higher. Oh, I think we have to see the video again. Sorry. But yeah, what happened at the beginning as well is that we didn't have the perfect parameters of the laser power that was needed. So as you can see on the left side here, we had the creation of bubbles. And if you think about building a road and riding your bicycle on a road with a lot of bubbles, I think that wouldn't be really fun. So yeah, we had to investigate and look at different parameters with our laser. And we went from, so we always had cracks, but we went from a very cracky, we call it space cookie structure, to some more flat structures that then have very defined cracks. And the cracks basically result because we have a material that's very similar to glass for their properties. There's also some metals in the powder, but yeah, at that point in time, we weren't able to avoid any cracking because of the high heat and then cooling down of the parts. So now we can look at a lot of images from our project. So you already saw the small samples. Obviously, that's not a road or a landing pad. Here you can see the larger box that we were then filling with simulant. You can see actually a video of the deposition of additional layers step by step. And then on the right side, you see actually everything together. We have the larger box in the mobile setup. We have the robot with the deposition next to it. And as you can already see, we then went ahead to melt not a road, but we called it single tracks. And as you can see here, it also cracked, but we investigated that it only cracked towards the end of the track where we switch off the laser and where we then have the cooling down phase. When we looked at multiple tracks, we also saw that then this wasn't true anymore. So on the figure at the bottom, you see the first track, and then the laser turns around and moves further to the left. It was just switched off, so it looks a little bit like volcanic lava or something. It's really cool. But you can see that then, due to this overlapping, we generated cracks in the first track again. So yeah, there was a lot of investigation in terms of the overlap that we needed. But in this next slide, actually in the picture in the middle on the right, you can see that we generated a track, and you can imagine, so this is maybe 20 centimeters long or maybe 25. You can imagine a small car from a kid driving around. So it doesn't have a lot of cracks, and it certainly doesn't have any bubbles. So yeah, this is really a good step towards having a road. What we also looked at in this project was to create geometries that could potentially interlock with each other, which means that then there wouldn't be a need for joining the different elements together because they would just organically interlock. And this is something that you can see on the right side of the slide. And if I go one slide further, we have this comparison of our idea that we had at the beginning, and then what we actually produced. And this project started in 2021 and is coming to an end towards the end of this year. So yeah, we really successfully produced these large components, and you have a bit of a size comparison here next to the elements, so that this is really a success, because on the bottom right you can see that they potentially interlock with each other, and that this could, with a little bit of adaptation, obviously create a road in the future. So, and what about the roadmap and the future? So talking about a demonstration mission and lunar landers, there are different options available. In Europe, we have the European Space Agency EL3 lander, which has a payload capability up to 1,500 kilograms, which sounds like a lot, but it's actually not if we think about the equipment that everyone in Europe wants to bring. So it obviously depends if there is space for such an experiment. There are commercial organizations contracted, and there is also the Artemis mission, and I think Artemis 1 is starting sometime in November. So this will be exciting, and Artemis Starship will potentially have a capability of over 100 tons. So this is a lot more. Yeah, so the main objective of our project PAVER would obviously only be a demonstration mission. So we want to show that what we have done in this project can also work in lunar environment, so that we can melt and sinter the lunar dust to produce elements with properties that are required for roads and landing pads. So we can't do this ourselves. That's why we look at government agency or commercial landers. And there are different options for this project to work on the moon. For this demonstration mission, we would either need to have a robotic arm on the lander, or we'd need to have a rover that is then moving across the surface. And there are other groups working on a rover already. So yeah, there is interest in this topic. What we'd also need, because we won't bring a powerful laser to the moon, we'd also need a solar concentrator to finally work with the energy of the sun. Yeah, this would definitely be possible pending mass budget and collaborations. And so the interest in lunar science has definitely seen strong revival in the last years, and not only by governments, also by commercial and, as we all know, private entities. So there is a lot planned for lunar vehicles that could potentially support a PAVER demonstration mission in the future. And with this outlook and these nice images, yeah, I want to thank you for your attention. I'm open to questions from the chat, or if you want to reach out, contact me or Jens Günster, who is leading this project, via email, and we can answer your questions or get in touch. Thank you very much.